Hello everyone, and welcome to our presentation. Today, I'm excited to share with you our machine learning project on a regression model for energy output prediction. In this session, we'll go over the main concepts behind the project, the methodology we used, and the key results we achieved. So let's get started. Let's take a closer look at the problem we're addressing. Our goal is to predict the net hourly electrical energy output, or PE, of a combined cycle power plant. To do this accurately, we need to consider various environmental and operational features that influence the plant's performance. Now, regarding our dataset, we have around 9,500 records sourced from CCPP data, which provides a solid foundation for our analysis. The key input features include ambient temperature, or AT, which affects how well the plant operates, exhaust vacuum, V, which relates to the efficiency of the exhaust system, ambient pressure, AP, that can influence the overall performance, and relative humidity, RH, which can also impact the energy output. Our main target variable, PE, represents the net energy output measured in megawatts, or MW. Understanding this dataset is crucial because accurate predictions enable better power generation planning, help optimize operational efficiency, and ultimately reduce fuel costs. So this slide gives us an overview of the problem, the data we're working with, and how these insights tie into broader business objectives. Now let's look at the problem definition. Our goal here is to predict the electrical energy output of a power plant, which we'll call PE, based on various environmental and operational factors. This is a classic supervised learning scenario because we already have historical data that's labeled, meaning we have features along with the actual energy outputs. Since we're trying to predict a numerical value, this naturally makes it a regression task. The target variable, which is the energy output, is continuous, so our goal is to accurately estimate that number. When it comes to evaluating how well our models perform, we'll use some common metrics. The mean squared error, or MSE, is useful because it heavily penalizes large errors, encouraging our model to be precise. The root mean squared error, or RMSE, is simply the square root of MSE and has the advantage of being in the same units as the output, making it easier to interpret. And then we have the mean absolute error, or MAE, which gives us the average absolute difference between predictions and actual values. It's also more robust to outliers, which can be helpful. Now, regarding the features we'll consider, we'll include all available environmental variables, like AT, V, AP, and RH, except for the target value itself. These features will be key in tuning our model's hyperparameters. As for the algorithms to try first, we'll start with a simple linear regression model. It's fast, interpretable, and serves as a good baseline. We'll also explore a random forest regressor because it can handle nonlinear relationships and complex interactions between variables much better than linear models. Finally, our overall modeling approach will involve testing these algorithms, comparing their performance based on the evaluation metrics I mentioned, and selecting the best one to accurately predict the power plant's energy output. Let's start with our data preparation strategy. I loaded the dataset into Excel and took care to ensure that all the values were numeric and consistent throughout. This step is crucial because clean data leads to more reliable models. The target variable we're focusing on is PE, which represents energy output. Since there were no missing values in the dataset, it means our data is ready for modeling without the need for imputation or additional cleaning. Moving on to how we split our data, we used an 80-20 split for training and testing. The training set, which makes up 80%, is used to fit and train our model. This is where the model learns the underlying patterns. The remaining 20% is our test set, which we'll use later for the final unbiased evaluation of how well our model performs on unseen data. Now, regarding validation, we employed a k-fold cross-validation with k equal to 5. This approach is more reliable than just doing a single train test split, because it provides a better estimate of how our model will generalize to new data. It involves dividing our data into 5 parts, training on 4, and validating on the 5th, rotating this process to cover all parts. This way, we get a more stable and trustworthy measure of our model's performance. In summary, our train test split ensures a clear separation between training and evaluation, while the k-fold cross-validation adds robustness to our validation process. Together, these strategies help us develop a model that not only fits our data well, but also generalizes effectively to new, unseen data. Now, let's look at our selected final model. We chose the random forest regressor because it achieved a lower MAE and better overall accuracy compared to the other models. As you can see in the table, the linear regression had an average cross-validation MAE of around 3.8 and a final test MAE of about 4, whereas the random forest scored approximately 2.3 in cross-validation and around 2.5 on the test set. We trained these models using Python, starting with linear regression, which served as our baseline. It's simple, fast, and easy to interpret. The random forest, on the other hand, is an ensemble model that handles nonlinear relationships well and captures complex interactions in the data effectively. The training process involved loading the data, then training multiple models with 5-fold cross-validation to ensure robustness. We recorded key metrics like RMSE, MSE, and MAE for each model to compare their performance accurately. Ultimately, we selected the best-performing model, which was the random forest. In summary, this comparison highlights how the ensemble approach of random forest outperformed the simpler linear model, especially in capturing more complex patterns in the data. This step is crucial in our overall goal of building a reliable predictive system. Let's take a closer look at which features had the most influence on our prediction. As we can see, temperature played the biggest role in determining energy output. That makes sense, since temperature directly affects how much energy our system can produce. Following temperature, vacuum conditions and other atmospheric variables also contributed, but to a lesser extent. This highlights how environmental factors, especially temperature, are crucial for accurate predictions. Understanding these key contributors helps us better grasp how different variables impact the overall system and reinforces the importance of monitoring environmental conditions in our models. Thank you so much for your time and attention today. I really appreciate you being here and engaging with the material. I hope this overview has given you valuable insights and a clear understanding of the key concepts we've discussed. Remember, the ideas we've explored are meant to inspire action and foster growth, so I encourage you to apply what you've learned. If you have any questions or want to discuss further, please don't hesitate to reach out. Thanks again for your interest and participation.